Good morning. Now we go to the second law. We now turn how the rider on the air track behaves when it is no longer isolated. What does means? If any body, any particle that is isolated, it will continue its own state. By the term isolated means there is no other interactions to that body. Suppose that we pull the rider in our linear air track experiment with a rubber band or a weight hanging from a pulley. As we see the pulley in the video. So we can choose the rider is pulling with a rubber band or we hanging a weight, from the rider to a pulley. It actually means we giving a force. Okay, our aim is to give a constant force to the rider. How can we apply a constant force to the rider? By these two methods. Consider the case of rubber band. When we stretching the rubber band more, we can give more force. The case of hanging weight, when we increase the weight, it will give more force. Okay. If the rubber band is very loose, nothing happens. we have to pull very hard to stretch the rubber band. Then the rider will start to give the constant force. To give the constant force, we must move our hand ahead of the rider so that the rubber band is always stretched to the same standard length as the previous. That is, when the rider starting to move, then what will be the length of the rubber band? Then we must maintain the same length of rubber band to ensure our constant force. So the rider moves in a wonderfully simple way. Its velocity increases uniformly with time. Okay, that is, we giving a constant velocity to the rider, then its velocity increases uniformly with time. The rider moves with constant acceleration. Just look at this video. Before going to the video, we can discuss what happened when we increase the weight of the rider, or what will be the change when we change this the rider. We use another rider that is bigger than the first. We change only the rider. We using the same rubber band and it is stretched to the same length as before. It means we giving the same force. We giving the same force to the new rider. Okay. Then we know that the rider will move with a constant acceleration, but the acceleration differ from the previous case. Here, what the changes? We changed the rider. It means we change or increase the mass of the body. Increase the mass of the rider and we apply the same force as before, isn't it? The same force as before because of the same rubber band is stretched to the same length. It ensures that the same force is given. So it causes a constant acceleration, but the acceleration is differ from the previous case. So the acceleration is, it depends not only what we do to the objects, but also on some property of the object. That is, here the change we done is we increase the mass of the rider, isn't it? The only change is increasing the mass of the rider, the same force is given. So we can say that the difference in the acceleration is due to this variation. So this property here, what is changed by us, that inherent property is called mass. Now look at the video. Here in the video, we use, instead of rubber band, a weight is hanged from the rider through a pulley, and the motion of the rider is noted, and we increasing the mass of the rider by inserting some weight on the rider. Just look at video. Here the rider is moving, and acceleration is noted, and next increase the mass of the rider by inserting weights on both sides of rider And again, the acceleration of the rider is noted. Here, the second case is done without changing the hanging weight in the pulley. That is, the applied force is not changed. The change in acceleration is occurred. It is due to some inherent property of the rider, that is its mass. We will use our experiment to define what we mean by mass. Consider the first case. We consider that in the first case, the rider has a mass. Rider has a mass m1, and when we applied a force, then it has some acceleration a1, and then we changed the rider, or in the video we insert some weight on the rider. So we take the mass of the second case as m2, and we observed the acceleration as it. Okay, so we can express the mass of the second body as the mass of first one into a1 divided by it. If we repeating the experiment with changing mass and observing the accelerations, we can define the masses as M3 is equal to M1 into A1 by A3. M4 is equal to M1 into A1 by A4, etc. By carrying out further experiment with the air tag, for instance, causing this type of motion using springs or magnets instead of rubber bands, we find that the ratios of accelerations, hence the mass ratios, are identical no matter how we produce the accelerations, provided that we do the same thing each body. Here we got these relations because of the mass ratios. That is, look at this one. M2 by M1 must be equal to A1 by A2. And here M3 by M1 is equal to A1 by A3. M4 by M1 must be equal to A1 by A4, etc. Thus, mass defined turns out to be independent of the source of acceleration, but it appears to be an inherent property of the body. So, mass is a measure of resistance of bodies to change in motion. That is, mass is a measure of resistance of bodies to a change in motion. Okay, in your +2 classes, we have come across inertia, isn't it? So we can say that the inertia is increasing with mass. Inertia is the inability of a body to change its state. Okay, now we go to define force. Here we use the same experiment done by us using the rubber and air track and rider. So we describe the operation of acting on the mass with a stretched rubber band as applying a force. What a force is? We said by stretching a rubber band, it gives some force. When we apply the force, the test mass, let it be the first mass, it accelerates at some rate e. It has some right, some acceleration, that is e. If we apply two standard stretched rubber bands side by side, that is, we pulling the rider with first rubber band and the same is done with another rubber band on the same rider, or we apply two forces, two same forces on the rider. Then we can say that the mass will accelerate with 2e. And if the first force is this direction and the second is the second stretch, the equal amount stretching in opposite direction, then the acceleration is 0. This the effect of rubber band. The effect of rubber band, it means the force that act algebraically, at least for the motion in a straight line. Here we consider the motion in a straight line. So here the effect of rubber bands add algebraically. We can establish a force scale by defining the unit force. We defining the unit force as the force that produces unit acceleration when applied to unit mass. We defining a unit force, that is the force that produces unit acceleration when applied to unit mass. From our experiment, that F units of force accelerate unit mass by F units of acceleration. That is, we give F units of force. We give F units of force to a unit mass. So it accelerates by F units of acceleration. Okay. Just look, if we give a force, let it be 2, an amount of 2 force. It may have any unit. 2 unit of force is given to a unit mass. Unit mass. Then it must have an acceleration because of this force is given to unit mass, then it must have unit acceleration, because a unit force on unit mass will give unit acceleration. So if we multiply it by 2, then this side must have multiplied by, okay, that is unit force, the force that produces unit acceleration when applied to unit mass. So when we increase the force, the mass is unit mass, then the force, the acceleration must be this type. Okay. So from this, we can say that the force F will produce F into 1 by m units of acceleration. Okay, here if it is force, here unit mass, and here it is acceleration. So we can say that the force F will produce F into 1 by m unit of acceleration when acting on mass m, or A is equal to F by m. In our familiar form, F is equal to ma. In the SI unit, the unit of force is Newton and the unit of mass is kilogram. Here the unit of force is Newton and the unit of mass is kilogram in SI unit, and the unit of acceleration is meter per second square. The unit of acceleration is unit of A is meter per second square. Okay, this is the second one. And we find that the force obey the principle of superposition. The acceleration produced by several forces acting on a body is equal to the vector sum of accelerations produced by each of the forces acting separately. By principle of superposition means the effect of individual will summed together algebraically. Okay, that the acceleration produced by several forces acting on a body is equal to the vector sum of the accelerations produced by each of the forces acting separately. Combining all the observation, we conclude that the total force F on a body of mass m is F is equal to summation Fi, where Fi is the ith applied force. If A is the net acceleration and Ai is the acceleration due to Fi alone, then we have F is equal to, then we have F is equal to summation I Fi, that is equal to summation I M Ai. As M is constant, we can return that M summation I Ai, that is equal to M E. This is the Newton's second law.